this lecture we will visualize the following function: g of xy equals cosine of x plus y plus sine of x times y minus 0.1 times square root of x minus y. As you can see, it is a function that goes from a subset of r squared to r. The codomain is r, and it is a subset of r squared because of square root of x. So square root of x will not have as an image a real number unless x is non-negative. Therefore, the domain of this function is a half plane where the first coordinate is non-negative and the second coordinate is unrestricted. Here we see a description, a visualization of the domain and the codomain. The domain is represented here on the left as this subset in a two-dimensional Euclidean space x, y, and the half plane we are looking at is this one that includes non-negative x coefficients. We also have highlighted in yellow the region that we will use in the displaying of the graph of g. Since the graph of g will be extended indefinitely for y, in order to make it more understandable, we will just restrict it to this rectangular region of the domain. Now the codomain is r, and one can show that the function is surjective, and therefore the image of the function is going to be the all infinite real line. So codomain of g equals the image of g. Let's see now the image of one point by the action of g. We have chosen a random point in the domain in this yellow region. So the point has coordinates 1.26, the first coordinate, and second coordinate 2.31. And if we apply g, we will be obtaining the following real number, negative 0.56. This is g of p, the real number we obtain applying g to it. I of p, remember that I is the map through which the map g, the function g, factors through. So g, we explained in a previous lecture, g, any function g can be factored through two maps. The first one being we called I, and the second one we called Q. And the set through which these map factors is the graph of the map. So in this case, I is going to go from the domain to the graph of g, and by definition of I, if we apply I to p, an element in the domain, its image in the graph will be the following pair. Let's say for the moment is pair of elements. It is p, so the element we are starting from is as the first coefficient, and then g of p as second coefficient. Now g of p is a real number, is negative 0.56, but p is a vector itself, so it has two components. Therefore, the image of p through I is going to be this triple of real numbers, 1.26, 2.31, and these amounts for p, and then comma negative 0.56, which is the image of p through g. So this is an element in the graph of g, therefore the graph of g will live in R3. This is a triple of real numbers, so it will live in R3, and we can actually draw it, as we will see in a few moments. Okay, so this is the image of about 15, maybe 10, 15 randomly chosen points in the domain in the yellow region, and we see that their images here, we cannot read anymore their images, but well, we still see a bunch of numbers, of real numbers. And from again, I want to stress the fact that from this representation of the function, we cannot understand anything about g. We cannot understand anything about the behavior of g, except on very few points we can randomly pick in the domain. Let's now construct the Cartesian product of the domain times the codomain, inside which we will represent the graph of g. Let's see how we do that now. We have seen it already for a function from R to R. Let's see how we do it in a function from a subset of R2, in this case, to R. The codomain, as you have seen, has been twisted and translated until the zero of the codomain coincide with the origin of the xy plane that inside which we have the domain of our function. So this is the setup, as you can see, in which we will draw the graph of g, and this is a classical three-dimensional Euclidean space represented through these three orthogonal axes, x, y, and, or if you want the vertical one, we can call it z. As a reminder, the name domain where it lies, and it is in the horizontal xy plane, and then we have written codomain in the vertical axis where it used to be the codomain of the function. So in this representation we see both of them at the same time, domain on the horizontal plane and codomain on vertical axis. Let's see a few points in the graph. Presented here maybe 10 points in the graph, according to the usual rule that we explained before. So the first two coordinates of each of these points are the coordinate of the element in the domain that generates the point in the graph, and the third coordinate, so the z coordinate, is the image, is the real number given by the image of the point in the domain. We cannot really understand the behavior of the function g from these 10 points once again. As we've seen before, seeing the points in the domain and their images in the codomain does not allow an understanding of the function g. Well, the same is true for the graph, but for the graph we can actually increase the number of points inside the graph in order to have a better understanding. So let's see what happens if we draw 300 points randomly chosen inside the graph. Okay, it is better than before, but still it is kind of shady. We don't really understand how g acts on the domain. Let's have again a spin around the z-axis to see how this cloud of points distributes, if there is any logic or anything, any particular shape. Well, we can actually something, but we don't really understand fully the shape of this graph, although it is much better than before. So let's increase now the number of points in the graph up to 12,000 and see what happens. So now 12,000 randomly picked points in the graph. Well, now it is much better, although from this perspective we can't really distinguish all the features. We do have a pretty understandable shape in front of us. Let's see around it how it looks like. this is what I meant when I claimed that the best way to represent all the information contained in a function g is to represent the graph as a subset of the Cartesian product of domain and codomain. We can see clearly here that gx on certain points, sending them to images that are higher than others, and it keeps changing, making all these waves up and down. You see that when it just dips underneath the zero, the xy plane, it looks like it's dipping underwater, and this is exactly what it's doing. So all the values that you see here in a less contrast region means that the image of the points in the domain that are generating these elements in the graph, the images are negative. Given a point in the graph, how to recover the element in the domain and its image that will generate this point in the graph. So let's see this graphically. So once again, we draw a yellow dot inside the graph, and we see the geometric construction to generate the point in the domain, which has this yellow dot as associated point in the graph. You see here? Okay, so we take the yellow point, we project it down to the xy plane. So this element here, which we have not represented with a point, but is just the intersection of these three segments. This is the point in the domain generating this point in the graph. The coordinates of this point are 2.61 x coordinate and 3.23 the y coordinate. Okay, so this point is generated by an element in the domain with coordinates 2.61 and 3.23, whose image is 1.90. This is the representation of the graph before in a more slim way, more accurate, not just picking up random points. What we want to do now is represent the associated point in this graph to the initial point P and its image that we have displayed at the very beginning of this lecture. Now the point is already there, but we cannot see it because once again is hidden somewhere. So let's move the camera in a way that we can peek and see exactly where it appears. Oh, you can see it. Well, the point P applying the map I will be sent to the point in the graph. So the point in the graph is the yellow one, and the point P along its image, which is hidden here, you cannot see it, give the coordinate to the element in the graph, just as we've seen before. So this is I of P. P is the element in the domain, and I of P is the element in the graph associated to it. You remember the coordinates of P were 231, it was the y coordinate, and 1.26 was the x coordinate, and the image was negative 0.56. Okay, so this is the construction of the element in the graph given the point P in the domain and its image. Now what we are doing is describe the map I on few hundreds, actually maybe few thousands elements in the domain, and see how I acts on them. Every yellow dot is an element in the graph which is the image of some element in the domain. So remember that I goes from the domain to the graph. So every yellow dot is being hit by some arrow starting from the domain. The elements where the arrows start from have not been represented by any point, because otherwise the image would have been too much troubled and hard to understand. The elements in the domain to which we apply I, the map I, are just at the beginning of these arrows. We just have highlighted the images in the graph. Okay, so this is the domain. The arrows go from the domain to the codomain, and these are the images. Let's see now the map Q that goes from the graph to the codomain. Again, about 4,000 points chosen in the graph, and to them we apply the map Q, and we will show where they go by means of arrows. So this is exactly what I meant. So there are several points in the graph, and the map Q just projects them to the the z-axis parallel to the xy plane, and each of the tip of the arrows represent the image of the Q map of some of these elements in the graph that we have chosen.